Okay, now that we know that vector-valued functions are a really good tool to describe the paths of particles in three-dimensional space, it's time to also look at how to describe the properties of the surrounding three-dimensional space itself. And in order to do that, of course, we will need multivariable functions, because if we want to assign a property such as a temperature to every point in space, well, that means we must assign a number, the temperature, to every three-dimensional point, which means we need to take triples of numbers, coordinates, and map them to other numbers, which are, in this case, temperatures, for example. For this presentation, we will start with functions of two variables, and that's because those can also be used to describe surfaces, and they're also used for bird's eye views, such as views of mountain ranges and things like that, and in fact, that's going to be our first example. Then we're going to talk about contour plots, which are that bird's eye view. We'll think about how time as an input can be digested. Then we'll talk about three functions of three variables, and then finish out with some technical aspects about domains, more variables, and compositions. Alright, well, let's get started, and let's start with something that actually is familiar and which answers a question that you may ask yourself at this stage, because every so often mathematicians will call functions maps. And well, if we look at that, this is a map, courtesy of the National Oceanic and Atmospheric Administration Central Library photo collection, and that is what people call a physical map, which is a map that shows a certain region on Earth, here the American double continent, North America and South America. And that physical map shows that region, and by using certain colors, it shows how high certain parts of that region are above sea level or below sea level. Hot colors typically indicate stuff that is high, such as here the Rocky Mountains. Then colors in the greens show things that are near sea level, and blue, various shades of blue, show what's below sea level. So that is something where this picture maps coordinates, right, longitudes and latitudes, maps coordinates to heights, which are indicated by colors. And so that is already something where this picture technically is something that takes two inputs, latitude and longitude, and maps every one of these pairs of inputs to an output given by a color, which is interpreted as a height. So that already is an example. Anytime you have looked at a map, you have looked at a function of two variables, at least when you've looked at a physical map. All right, so when we're looking at other functions of several variables, just to set the stage, basically anything that varies in time and space is technically a function of these variables. So temperature varies in time and space, pressure varies in time and space, concentrations of substances, if you are looking at chemical situations, or dissolutions of sugar in coffee and things like that, is also something that varies in time and space. Radiation levels are varying in time and space, and so on and so on. The number of variables that we use certainly depends on the model, because if we're looking at a temperature map, for example, again for the North American and South American continents, then certainly we could get away with a flat map and just indicate the temperatures by colors, because typically we are interested in temperatures at the surface of the Earth, and we're not too interested in what happens 10 kilometers above, even though aviation people are certainly interested in that. So then also, if we have a snapshot in time or a steady state, we will not need a time variable. So for example, a physical map, even though we know continents migrate, a physical map doesn't need a time variable, because for our lifetimes that is not terribly relevant. And yeah, if the dependence on the height is not of interest, so for example, for that weather map that I mentioned for ground temperatures, we would not need a z variable. And typical for a weather map, we also take a snapshot where people talk about the daytime high temperatures, for example. Alright, so now let's actually set up a definition. A multivariable function f assigns to each point x, being x1 through x in an n-dimensional domain, a real number f of x, which is f of x1 through xn, so this x is a point and therefore has n coordinates. Okay, so that's the definition of a multivariable function, and you can see that this is pretty much the definition of a function that we know from single variable calculus, only now we have n inputs rather than just one input. In fact, if you suppress the fact that x is now a point in n-dimensional space, it would be exactly the definition that we know already. And similarly, the definition of a graph of a multivariable function, a function of n variables with domain D, well, that is a set of points x1 through xn, f of x1 through xn in n+1 dimensional space, where x1 through xn varies through the domain D. And if we want to look at the graph visually, the best we can do is that we look at a function of two variables. So that's what we're going to do. We give ourselves our right-handed three-dimensional coordinate system. And then our domain, if we want to have a generic picture, we just use a square or rectangular domain. And the graph is now a set of points above that domain. So we go above that domain, and basically the graph is then some kind of surface as indicated here. And if we want to evaluate the function at this point, which has coordinates x, y, then very similar to what we do for function of one variable, we go up to the graph where we encounter a point, and from that point we go over to the z-axis this time around, and the value on the z-axis that we obtain is f of xy, and the point, of course, is xy, f of xy, which is exactly in keeping with the definition of the domain, as we can see here. Sorry about the highlighting there. Okay, so that is the definition of a graph, and this kind of plot is what we will actually call a surface plot. And so now it is time to just start, and we're going to start with things that we can still draw in 3 dimensions. So we will start with variables, with functions of 2 variables. So the idea for functions of 2 variables, well, there are 2 things that we have to do. We have to be able to read the graphs, and we've seen how to read that graph on the previous panel, but we also want to know how to create that graph. And in order to do that, it is typically sensible to look at vertical cross-sections, because if you look at a computer plot of a function of 2 variables, such as this paraboloid here, well then very often, or typically even, you will see that there is a grid on that plot, and that grid comes from the following. If you have a function f of xy of 2 variables, then the trace in y equals k is the single variable function f of xk, where k is a constant. So basically, the lines where x varies and y is constant, the lines that are coming at you, those are the traces in y equals k put into space. The trace in x equals k is the single variable function f of ky, where k is a constant. So the ones that come at you the other way, where we have x being constant, those would be the y traces. And those traces together, of course, form a mesh that give us a pretty good idea of what the graph looks like, right? So these traces are also called the x traces of f for x constant, and the y traces of f for y constant. And the way they can be used to actually draw a graph is shown here. If you take the x traces and the y traces and put them together correctly in space, you ultimately get exactly the picture that we had on the previous panel, right? So that means if somebody gives us a function f of xy as an equation, if we can get the x traces like this, and if we know what those look like, and if we also can figure out what the y traces look like, and if we can put those together in our minds in the right way, then we get a pretty good picture of what the graph looks like. So these are good visual tools. To really just more firmly establish these idea of traces in our minds, let's look at those in two more ways. The x traces are always obtained as intersections with a vertical plane. So a vertical plane would come down, and the intersection with that vertical plane is the x trace, which is on the right-hand side here, placed into space in the right place. So that's how we get x traces. If we want to look at the x traces in a different way, if we want to look at those like in, say, a CAT scan, where sometimes you just have something that traces your whole body and takes pictures all the way along, well, that's also what the x traces are, because as we take this plane moving along, we get different types of intersections of this paraboloid with this vertical plane, and those intersections, if we were to now just put these traces together, basically smear them out again, we would get exactly this plane. So this is another way to visualize what X traces are and what X traces do. Once we've got that, Y traces, of course, are very similar. Y traces are just intersections with vertical planes that come at us in the X direction. And again, we get the intersection and we get the trace, right? And then if we want to go to the, okay, one more time, intersection and trace. And if we want to go to this CAT scan idea, well, we just have a plane that now moves along the x-axis. It's a plane, along the y-axis, it's a plane y equals constant. And as that plane moves along, we get different kinds of intersections. And if we know what these intersections look like, we get a pretty good idea what the graph should be. Because if I were to just show you the right-hand side here and say, put this in your mind together as a picture where this smears out, you would pretty much get this picture. Okay, so as an example, we can use traces to sketch graphs. So let's use traces to sketch the graph of the function f of xy equals 1 over 1 plus x squared plus 4y squared. Well, the x traces would be the functions f of ky, where f of ky is 1 over 1 plus k squared plus 4y squared. And we just bracket the 1 plus k squared together. And so basically what we have here is 1 over number plus some number times y squared. So this is sort of like 1 over 1 plus y squared. Okay, the 4 would be disregarded there. But we know what 1 over 1 plus y squared looks like. That's some sort of a bell curve. The 4 squeezes that bell curve together a little bit, and the 1 plus k squared then just governs the height of that bell curve a bit. And so this is 1 over ak plus 4y squared, which are those bell curves, as I mentioned, which, because ak is 1 plus k squared, those things are tall for small k squared, because when k squared is small, we get a 1 here, whereas when k squared gets larger, we get a larger number here, which flattens out the curve. So overall, these x traces look like this. And that's, of course, a pretty demanding movie to just visualize in your mind. So what you would probably want to do if you have to sketch that, you would just want to sketch a couple of those traces. But basically what happens is that, okay, let's let it get down first again and then start over. What happens is that for k negative, well, k squared makes that positive, so we divide by a pretty large number, so we get a flat bell curve. As k squared gets small, so as k gets towards 0, we get taller bell curves. As we can see here also, the maximum is at 0, or the tallest curve is at 0, and then it flattens out again. So if you were to put this picture into your mind and think of how this develops in space, that would look sort of like a fin, right? And of course we can also do this with the y traces. And f of xk, well, that's 1 over 1 plus x squared plus 4k squared, so that's 1 over 1 plus 4k squared bracketed plus x squared, which is 1 over ak plus x squared, so that's exactly the function 1 over 1 plus x squared, only that ak can get larger as k squared gets larger, so as k gets away from 0. So the y traces are bell curves that because ak is 1 plus 4k squared are tall for small k squared, and otherwise they flatten out. And they are wider than the x traces, and that's because the x squared is not multiplied by a number. So that means the y traces are something that is a little bit wider, but overall it also gets tall and narrow again. And so basically this is something where if we stay with this idea of a fin shape, this is something where we go over the fin in the other direction. And what you then mentally and also physically, if you've got a direct drawing task that says draw this thing, then you would do this directly in space. When you draw this, well, you draw the x traces, which are the flat bell. Well, you draw the, hang on, let me get my vocabulary straightened out. This one first draws the y traces. Those are the tall ones. Then you draw the x traces. Those are the flatter ones. And, well, then you interpolate and you get the graph. Okay, now let me get this straight one more time. It really doesn't matter what you call what. You've got one set going one way, the other one going the other way. You just have to get the name right. So the y traces are the one where y is constant, right? And so those are the the flatter ones, and the x traces are the ones where x is constant, and those are the taller ones. And if you put those together, as we do in this graph, here are the y traces, and then here you get the x traces, which are the narrower ones, and you really get exactly what I promised you. You get this kind of fin shape. So this is something that is a really nice tool to draw functions of two variables, and it makes for nice animations and things like that. Well, typically, of course, this is what a computer does when we draw contour plots, as they're called in a computer. It's just by now computers are so fast that you don't see the explicit drawing anymore. Remember, I grew up with slower computers. I'm not sure I ever drew a wrote a three-dimensional drawing program, but the first three-dimensional drawing programs that I saw definitely took some time to actually generate that mesh, and you could literally watch as the mesh was generated in real time. Okay, so definition. This picture that we've just obtained by drawing the mesh of properly positioned x and y traces, that is called the surface plot of the function. Makes a lot of sense, right? Now, these surface plots can be modified in many ways, and we're going to take a look at that in just a minute. But basically, the presentation of graphs with traces is similar to the 6 principal views of an object in technical drawings. So, if we are taking a surface plot, well, then first of all, that just shows a pretty three-dimensional, a picture that is meant to be three-dimensional. Of course, in technical drawings, we typically just look at things down an axis. So if we were to do a technical drawing, we would see the straight down view down the x-axis. We would also see the view down the y-axis. We would also see the view from behind. I'm going to spare you that right now. And then we would also see the bird's eye view. And if we're looking at the bird's eye view, well, that bird's eye view doesn't really tell us very much, at least in this kind of coloring. And so what we can do with a surface plot, like I said, a surface plot can be drawn in many ways. And so, for example, I could change from solid color, which is really nice to make images that look really nice in three-dimensional, to color map. And what that does is it gives us a plot that is more like the plot that we have seen for the physical map. It uses cool colors to show regions that are lower down, and it shows warmer colors for regions that are higher up. And so now, if we were to again go into the bird's eye view, we would get a bit of a better impression as to what this thing looks like, because now we know this is lower down and this is higher up. And if we have that, then we might as well forego that square mesh and actually go to what is called a contour plot, which is the next thing we want to look at anyway. And so for a contour plot, then I also want to have contours filled, and I want to have a color map there. So if I apply that, then I end up with a color map with a contour that is very much like a physical map, where again cool colors show regions that are low down, and as the colors get warmer, you get stuff that is higher up. And then of course you can see here that for symmetry, this isn't as interesting as it would be if we were to go from -2 to 2. So I could also do that. I can go from -2 to 2 in both directions, and then I also have to change, okay, the axes are auto-scaled, so this will give us now something that really shows this paraboloid in a in a more symmetric setting. And the typical thing, however, that happens is that we don't fill the contours, and that we have contour lines in a color map, which basically is the situation that we can often see on a hiking map, for example, where the contours themselves are just colored, and that's where we get back to the presentation. And so here we are back. So let's now take a look at contour plots. Contour plots are also something that you have seen before if you've ever gone hiking or driven in an area that is mountainous. This picture is courtesy of the U.S. Geological Survey, and it shows a part of the Grand Canyon where the Colorado River is in the center, of course. And every one of these lines here shows a different height, and every so often a thicker line says, okay, this contour line here, that's 1250 feet above sea level. This thicker line here is 1,000 feet above sea level, and it goes, I think, in steps of 50 feet, because you ought to have 4 contours in between for 1,050, 1,100, and so on, and so on. And a hiking map such as this one, as soon as you're experienced in reading these things, and if you aren't, you will get experienced, because we will look at these things as contour plots. Well, once you're experienced in reading these things, you realize areas where there are no contour lines are fairly flat because they are between consecutive contours. So that means that height in these areas does not vary more than 50 feet. Whereas where contours are really tight together, yeah, that's the kind of stuff where you either have a very steep path, or you basically want to stay away from it at all, because this looks at some point in time very much like a cliff, right? And cliffs, well, okay, if you can handle heights, it's not going to bother you too much, but still, a cliff is dangerous, because if you step in the wrong direction, you could fall off. So that's something where you hike with care, even if heights don't bother you. All right, what does that have to do with mathematics? Well, the definition is that for a function f of xy of 2 variables, and remember, height above sea level is a function of 2 variables, right? The trace in z equals k is the solution of the equation f of xy equals k. Even though we don't think of hiking maps in these technical terms, basically, the contour that says here's the height 1,250 feet above sea level, that is the solution to the equation. Take heights above the earth and solve for height being 1,250, right? And that's where k is a constant, of course. And the traces are also called z-traces, or contour lines, or level curves. And if we take these things and put them together into a picture, the picture obtained by drawing the level curves for equally spaced values of the z value, that is called the contour plot of f. And of course, we have seen that already. We have seen the contour plot for that paraboloid as I showed it to you in MathCAD. And so basically, if I want to put some values to it, we would have a bunch of contours, and then this top height here is 9, and then every 2 contours I give you another height. So this height is 8, 7, 6, and so on. And we have already seen what that thing looks like in 3 dimensions, but basically, if you really have good visualization, or if you abuse yourself long enough and then make an animation like that, as I have done, as I was abusing my mind trying to figure out how exactly to explain this stuff. If you want to visualize a contour plot, basically what you have to do is you have to stack the contours back up, and as you do that, you can literally, if you've got good enough visualization skills, or if you just have something that's simple enough, you can see what this thing looks like in 3 dimensions. Now, as a quick disclaimer, when I look at a contour plot of the Grand Canyon, I don't see those things stacked back up to what the Grand Canyon actually looks like, but I can read the contour plot, and that's the most important part here. So there is a fine line between training your visualization skills and actually really just trying to abuse your mind in ways that it's not meant to be used. And so this is something that is somewhere in between, even though I think that animation is just really, really cool. Okay, so we move on, and we still talk about the contour plot. The level curves, how do you obtain the level curves? So far we have talked about reading contour plots, right? How do you actually obtain a contour plot? Well, the level curve is basically the intersection with horizontal planes. So if you have, again, this paraboloid, then you intersect it with a horizontal plane, then here is one of the level curves. Intersected with another horizontal plane, here's another level curve, and you intersect with another level curve, and you get another horizontal plane. So that's the idea for this example, where if we were to sketch the contour plot of this shark fin function, if you will, that we have already looked at in terms of surface plots, then what we need to do is we need to find the contours, and we do that by setting f of xy equal to k. And that would mean that 1 over 1 plus x squared plus 4y squared is equal to k. Well, that would mean, if we take reciprocals, that 1 plus x squared plus 4y squared is equal to 1 over k. And if we bring the k over, we get that k plus k times x squared plus 4k y squared is equal to 1. And then I bring the k over, so that's kx squared plus 4k y squared equals 1 minus k. And now I can just divide by 1 minus k, even though I'm not going to do that quite yet. Basically what this shows is there are no contours for k strictly greater than 1, because the sum of squares can't be negative. In fact, we could say k greater or equal than 1 if we don't accept point-shaped contours, which we sometimes don't. And for k smaller than 1, well, for k smaller than 1, I can divide by 1 minus k, and then by also bringing the k in the denominator, I get equations of ellipses, right? X squared over 1 minus k over k plus y squared over 1 minus k over 4k equals 1. Those are ellipses for k smaller than 1. And the x radius is greater than the y radius, because this here would be the length of the major axis in the x direction, or the square of the length of the major axis in the x direction, which is longer than the length of the major axis in the y direction. And so that means the contour plot, I have to go back to MathCAD just to a different window. You could show, you could draw some concentric ellipses if you wish, or let's just go over it one more time. If the way we transition from the contour, from the surface plot to the contour plot, we go to a bird's eye view of the surface plot that already has the right kind of coloring. And then, of course, if you squash all that down, which is what we plan to do here, we go to the contour plot. We get the contour plot now with the x-axis actually going across. And I could say that I want to have a color map on the lines, and we get the colored contour plot. And these aren't quite ellipses, but that's basically just because we don't have a fine enough mesh. So if we go to a mesh of 100 by 100, the problem then is that it takes a little while to draw. Okay, it doesn't take that long, but here we actually get the concentric ellipses where the quote-unquote x radius is larger than the quote-unquote y radius. All right, so we have drawn the contour plot there. Of course, by hand, you would just have to draw some concentric ellipses showing that the heights are higher near the center than they are on the outside. Okay, another example. Okay, now we're going to talk about time as input. Here's where we really are just going to do visualization. So as an example, take a look at a vibrating string of length 1, and if you don't know what a vibrating string looks like, hey, look, grab a rubber band and snap it a little bit so it vibrates. That is modeled as follows. Each point on the string has an x-coordinate in the interval 0, 1 and a vertical displacement u from equilibrium. We assume that the displacement is given by the function u of xt being sine pi x cosine pi t, with 0 smaller or equal x smaller or equal 1 and t greater or equal than 0, where x is a space variable and t is time. And we just want to explain the physical meaning of the traces of u. We really are working our way through all sorts of functions of several variables, and so that the first thing that we really just need to do is explain what those things are. So if we are setting t equals constant, then we just get a function of space. So we're basically getting a snapshot in time, and what we're getting are sine functions. We're going with x from 0 to 1, so that means the input of the sine function goes from 0 to pi, so we just really just get a upper or lower wave of a sine function that is scaled in a certain way depending on what the cosine pi t gives us as an amplitude factor. So those are snapshots in time. And the x traces, well, if I set x equals constant, then I'm basically fixing a point on that string, and so those show the motion of a particle at position x over time, because now time is the variable that runs. Okay, so that means the graph really is a movie. And what do we have here? The movie is that this is basically something, that's how a vibrating string really could look like. It goes up and down, and without friction it would continue oscillating like that forever. The individual t traces, then of course, if I just stop the movie, I realize that at t equals 1.76 I get this snapshot, and that's a t trace. If we're looking at the x trace, well, the x trace is drawn over time, because what I have decided to do here is I decided to trace the particle at x equals 1/4, which is the one that is right here, and it's going down, up, down, and back up. And you can see on the right side the trace is being drawn as time proceeds. And of course, the trace itself would be the trace that goes throughout time completely, and so that would be something where I'd have to stop right here, and then this would be the x-trace. So when time is involved as an input, then holding time constant gives us a snapshot. That's something we want to remember. And if we don't hold time constant, then we get the development over time of a point or maybe several points, because what could also happen is that if we have two space variables and one time variable, if we let time run, then we get something like a movie of a vibrating drum membrane. And this is really something where if you take high-speed images of a vibrating drum membrane, this is one of the modes in which a drum membrane can vibrate by itself. And so then you basically get a movie where you at least show a two-dimensional, well, here just a two-dimensional surface, but that is already embedded into three-dimensional space, because what we're showing here is a surface plot as it develops over time. So for okay, so basically for any time we've got a time variable involved, we basically have a movie. So in particular, anytime you have watched a movie, you basically have watched a function of three space variables and a time variable. Let's take a look at three variables. Well, if I want to look at a function of three variables, then basically I have to draw certain kinds of surfaces, and we're going to talk about parametric surfaces in just a minute, or in the next presentation actually, which will hopefully be in just a minute for me. But basically what you have there is, for a function of three variables, well, you could say, all right, this may be a function here that is constant on this surface of a sphere, and as soon as you draw that surface, well, you can't look inside anymore, so you have to deal with the cutaway. And then if that function is constant on another sphere, well, then you can't look inside that, and so you need another cutaway, and then another cutaway to show the inside there. And so basically, when you have a function of three variables, typically people draw some kinds of cutaways where the surfaces show layers that have where the function assumes the same value, and the colors indicate the values, and again, hotter colors indicate higher values, and cooler colors indicate lower values, which is something that you may have seen in a science article, for example, when people talk about the structure of the sun. And this is an image that is credited to NASA, which I got off of their site, and it's exactly this kind of thing, right? It's a cutaway, and the various layers that are given the same color show you similar geological layers on the sun this time around, which then also have different temperatures, for example, and so different colors here indicate different layers, indicate different properties, and those properties would be a function of three variables. So the mathematical definition is that if you've got a function of three variables and k is a number, then the solution set of the equation f of x, y, z equals k, that is called a level surface of f, and those level surfaces, again the NASA image, those level surfaces are then typically given to us as cutaways, and that means we also need to think about general surfaces in three-dimensional space, and that's what we will do in the next presentation. As an example, well, for the function f of x, y, z being x squared plus y squared over 4 plus z squared over 9, we want to classify the level surfaces. Well, x squared plus y squared over 4 plus z squared over 9 set equal to k. Well, we can divide by the k and then sort things out a little bit. We get x squared over square root k squared plus y squared over 2 square root k squared plus z squared over 3 square root k squared equals 1. That sort of looks like an ellipse, except that we've got a third variable, and that means that this is really, if you haven't worked with quadratic surfaces yet, we will also talk about those explicitly in another presentation. But basically, this is an ellipsoid. It's the three-dimensional analog of an ellipse, where the radius in the x direction is root k, the radius in the y direction is 2 times root k, and the radius in the z direction is 3 times root k. I'm talking slang here. Those are actually major axes, but look, I mean, words are words, pictures and concepts are what's important. And so if we want to look at this thing, what we realize is that these level surfaces would be something where the diameter in the x direction is smaller than the diameter in the y direction, which in turn is smaller than the diameter in the z direction, but that is only one level surface, right? And so if we then do the cutaway again, we see there's another level surface, which pretty much looks like the previous one, only scaled down, and inside that there is yet another level surface. And so that would be that we have classified the level surfaces and then also drawn them. The drawing typically is done with a computer algebra system, and that is then also certainly preferable for a lot of things. You want to be able to visualize these kinds of things in your mind. Now, that sounds really scary because I'm throwing a lot of stuff at you, but believe me, as we go through this over and over and over again, you've already seen that for when we talked about curves in space. We wanted to have all the visual concepts up front, and then we visualize them step by step over and over again. With this repetition, we will build those skills. Okay, so now we're coming to the abstract mathematics here, and surprisingly enough, that's actually going to be easier. If we're looking at the domain, for example, the implied domain or natural domain of a multivariable function that is given by an expression is the set of all numbers for which the expression can be evaluated, or the set of all tuples of numbers if we want to be completely careful. And that's the same idea as for single variable functions. If I just suppress all the references to the fact that we have multivariable functions here, this is exactly the definition of the implied domain for single variable functions, and that means it can't be that hard. So if we were to find and sketch the domain of the function of two variables f of xy being square root of x squared x minus y squared, well, what do we know? The only things that can go wrong with domains are divisions by 0, which don't happen here, or that you've got negatives under even roots, and so we must make sure that x minus y squared is greater or equal than 0. Well, that means that x is greater or equal than y squared, and so that means the demarcation line in a regular xy coordinate system, of course the domain, of course, is a two-dimensional object now. The demarcation line is the standard parabola, except that it's opening to the right because we're looking at x equals y squared, right? And then x greater or equal than y squared is the domain, which means this stuff here is ruled out, and the domain is just this region here. So then you have to make sure you indicate your convention that this stuff that is marked is not in the domain, and the domain is actually over here. But that would be a good picture of that domain. The only other thing that could go wrong in a domain is that things could have a division by 0. If we're looking at functions with more variables, well, the visualization is context dependent if it is possible at all, right? If I've given you those cutaways for functions of 3 variables, as soon as we thought about layers in the sun, that certainly worked out rather nicely. But if you've got a function of 4 variables, then you would have to think about how those layers develop over time. Then things get really complicated. Physical quantities typically depend on space and time. So typically, well then first of all, there is a technical consideration, and that is in computation for these quantities, we drop the arguments because writing out all arguments would make formulas hard to read. Look at your physics classes. If you're looking at an equation like the natural gas law, PV equals nu RT, well, nobody is going to put arguments x, y, z, and t behind the pressure, the volume, and the temperature. That is just something that is assumed that people know, and we will also go with that convention and typically drop the arguments because otherwise our formulas would be way too big. So it's going to be a challenge, and it's going to be a challenge also from a visual level because if you've got functions that depend on time and space, those things are movies. But we are there, right? So there is nothing that we could do to make things more complicated than reality, or at least it shouldn't be, because the purpose for just about everything we do with calculus is to describe reality, to do physics. So we have arrived, right? We've already seen. What have I shown you? I've shown you surfaces in space. I've shown you mountain ranges. We talked about time as input, where we've got vibrating strings, vibrating drum membranes. Those are all real objects. We've talked about 3 variables. We've talked about geological layers, and so on, and so on. So we really have things that make sense in real life. We just have to work with them. And finally, we're going to talk about composition real quick, because as we started, this is sort of a good bookend because we started talking about by talking about how particles paths are described by functions, by vector-valued functions, and of course particles then travel in an environment. And so then what you'd like to know, for example, is you'd like to know for the function f of x, y, z, which may describe something like a temperature. Note that there is no explicit dependence on z, which is fine. And a curve, c of t being e to the negative t cosine t, e to the negative t sine t, and t, which may be the path of a particle. We want to find the composition f of c of t. We want to plug the curve into the function, which would then tell us, if we keep thinking of this f as a temperature, it would tell us the temperature at the position of the particle at time t. That is something that is certainly interesting when you're tracking objects that go through various layers of temperatures, like airplanes or space probes that are being launched, or now, as I record this, the next rover on Mars has just landed, Curiosity, right? And so that one also, you have to keep track of what the temperature at the position of the rover is, because if it gets too cold, you probably can't do certain things anymore and may need to shut down certain functions just to protect them. All right, either way, the composition, well, what's composition? Composition always was that we plug one function into another function. Now we have a vector-valued function plugged into a function. Well, that just means that x of t goes in for x, y of t goes in for y, and z of t goes in for z. So that means this is f of e to the negative t cosine t, e to the negative t sine t, and t. And that is just that we plug in e to the negative t cosine t for x, so we get e to the negative t cosine t squared. We take e to the negative t sine t, plugs it in for y, we get e to the negative t sine t squared, and we take the square root of the whole thing. Note that in this case, z of t equals t is not used. That can and does happen, and when it does, we're actually quite happy because we've got one less variable to keep track of. Other than that, it's just that we're working with algebra now, so we square all this stuff. We realize this is the square root of e to the negative 2t cosine squared t, because e to the negative t squared is e to the negative 2t. And same thing here, e to the negative t quantity squared is e to the negative 2t times sine of t squared, which is sine squared of t. Then we can do some more algebra, because if we factor out the e to the negative 2t, we have cosine squared t plus sine squared t, which is 1. So this is just the square root of e to the negative 2t, and we can take that square root, so that's e to the negative t, and that's it. Okay, well, you've seen it one more time. Multivariable calculus is about visualization and then handling a couple of computations. Of course, the computations will get more involved because ultimately we will also have to do calculus with those things, but as you have seen in this calculation here already, you just have to keep track of the entities, take your time, make sure you substitute everything in right, do your algebra. There is nothing new here, it just gets a little bit more complicated. And you have also seen certainly a lot of really cool visualizations. And I hope I've given you a couple of anchoring points for the visualizations, such as maps, such as geological phenomena that you want to keep track of with cutaways, such as movies literally, so that you have a good basis for visualizing the various physical contexts that we're also going to analyze and also use as anchoring points to understand, give meaning, give visualizations to all the mathematics that we are keeping track of in multivariable calculus. However, for now, you want to do some homework, you want to face the visualizations, face them down, put them into your mind, and then continue with parametric surfaces, which are up next, I think. All right, good luck and have fun.